So Zoomers, are you able to see the crazy animation?
Yep.
All right, and then out here live, you can see it as well, right? Okay, so I know this is going to sound a little bit crazy, but my goal is you could hopefully understand a lot of what is going on the screen by the end of tonight's lecture. Now, what? Sign me out. Shoot, it's my meeting. Well, hopefully this is still streaming. Hold on, maybe possibly technical difficulties here. Let me.
The stream on YouTube's working, so I think you're good.
Okay, all right. It's just telling me I'm logged out, but
Yeah, it's all working, so.
all right, I'm going to log back in just in case. Whatever. Okay. All right, I don't know what happened there, but strange. I'm getting something weird on this screen now. Yeah, it says it's live, so we're going to go with it. All right, sorry about this. It's always something at the beginning, isn't it? I just want to make sure this, I've got this YouTube running here. All right, I guess if it starts talking to me, we'll know. All right, so our goal here is to try and understand as much of this picture as possible tonight. I don't know what happened there. There it goes. Always something. All right, then I guess I'd better annotate on this screen so that the Zoomers can see what you could see. So there is a lot going on in this picture, and I want to try and talk about some of the terms. And if you want to, you can have your book open to, I believe, page 199 and 200. So take a second when you have your workbook open, look at both pages for a second, just so you can see that there's a bunch of equations on both pages. 199 and 200, I think I said, yes. We're gonna, so there's a lot of equations here. Most of the equations are on page 200, and most of the conceptual knowledge is on page 199. All right. And then, so just be aware that's there. If you want, you can ask me questions about anything. All right, so first thing I want to talk about is these voltage numbers, and I'm going to circle something. Maybe we'll go with, let's go with this blue color here. Let's do, all right, we're going this way. I want to look at this number right here. The V0 equals 8, and this number right here. Now, I haven't explained this at all, but I want you to know that V RMS is equal to V naught over root 2. So I haven't explained why that's true. I can do that later, but it's going to help us understand this. And what does V naught mean? V naught is called source voltage amplitude. So I'm going to call it source amplitude, all right? And since it's a voltage, I'm going to call it source voltage amplitude. But basically, it's source amplitude. I'm going to leave that up over here just in case you need that. And I'll explain what that means. Sorry, I'm so slow. Okay. Look at this sine wave right here that I'm circling. Do you see the orange sine wave at the bottom?
Yeah.
Right here. What I mean is the amplitude of that is 8, but the root mean square value is 5.66. So basically, if you take the amplitude and divide by square root of 2, you get 5.66. So sometimes people are going to say that's an 8-volt sine wave, or sometimes people say that's a 5.66 volt sine wave, RMS. So it's just basically, I hope you agree that stating the amplitude and the RMS value are basically telling you the amplitude, right? You can get one from the other. Everybody okay with that? Notice that's going to be important because all of the numbers here are written in terms of RMS. See how there's an RMS on all of the current voltage and all these different terms. So basically, do you agree that's like telling you the amplitude of each of those waves within a factor of square root of 2? So the only place where they don't use that square root of 2 is right down here where they said it's 8 volts. Okay, they set the volume knob to 8, which is on average, root mean square, these values. Okay, and now what I want you to do, let me get this out of here. We know what RMS means, it's just some number. I'll explain why it means that number later. Now I want you to look at these two things right here, the source voltage at the bottom and the current. Okay, notice the source voltage is a sine wave or a cosine wave, however you want to think about it. The current is a sine wave or a cosine wave. Now, what I'm going to do is I'm going to adjust the frequency, and I want us to look at these things. All right, so as I adjust the frequency, watch what happens to the source voltage. It changes. Do you agree? Does the amplitude of the source voltage change? No, the amplitude is always 8 volts. Said another way, the RMS value is always 5.66. Now, when I change the frequency, that's changing how frequently we get a crest or a trough. All right, that seems reasonable. Basically, changing the frequency, changing the period, same thing, right? Okay, now pay attention to the current. How much current amplitude do I have at very low frequencies? Not much. And again, we're looking at, sorry, I got to do this on Zoom here, but we're looking at this one right here, right? Do you agree that's a very small amplitude or very small RMS value? Okay, now as I ramp it up, do you agree the amplitude or the RMS is increasing? We see it's going to reach a peak somewhere right in there. Then it's going to start getting smaller again. Agreed? Okay, so that's one thing to notice. The other thing I want you to notice that's kind of difficult to talk about is I want to talk about the phase angle. In particular, let's just look at, I'm looking at these two curves that I've circled here. Let me, hold on, let me get this up here. Okay. So I want you to look at this curve right here and this curve right here, and I want to look at, do they peak at the same time? Do they hit the crest at the same time? What do you think? No. No. Which one hits the peak first? Does it? I'm going to talk about the current. So I'll tell you, actually, I'm going to talk about the voltage. Watch the current, and I will talk about this one. So voltage hits peak now. Voltage hits crest or trough. Voltage hits peak. Voltage hits trough. Do you agree the current is actually hitting the peak just before? Is everybody okay with that? So in this, I claim we just noticed that the current is actually, this is very different than resistor circuits. With resistor circuits, if you had more voltage, you had more current. Here we're seeing that when the voltage is low, you get a lot of current, and oh my gosh. Okay, more on that in a minute. What do you think is going to happen when I crank the frequency? The frequency is cranked now. Which one is peaking first? Can you tell? So I'm going to say the voltage peak for you. So peak, 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 peak. No, they're not the same. Look, this is peaking slightly first. So watch this one. I'll say the words peak. Oh, sorry, on Zoom. Watch the current, Zoom. So Zoomers, watch the current, and I'll speak out the peak on the RMS for the voltage. Peak, 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 peak. Do you see the current is a little behind? Just a tiny bit, but it is behind. So notice sometimes the voltage peaks first, sometimes the current peaks first. Do you agree? All right. Watch what happens if I go to some special frequency that gave us the max. What was the maximum? It was some right about here, right? Now look at them. Do they peak at the same time? Yeah. So sometimes the voltage peaks first, sometimes the current peaks first, sometimes they peak at the same time. This is complicated. We're going to discuss this. So we like to use phase angles to describe the difference between when they peak. More on that in a bit. Okay. All right. So now let's go to this interesting fact. What's the source voltage? Remind me, what was the number for it?
8 volts.
It was 8 volts, amplitude, 5.66 RMS. Look at the voltage across the capacitor and the inductor. You apply 5.6 volts or 5.7 volts, and you get 35 volts across the capacitor and the inductor. Isn't that odd? We get more voltage. But have we seen something like this before? Remember when we did the inductor and you could pull the switch and then you got a giant voltage spike? So sometimes, and in that one, we got like 10 times the battery voltage. So sometimes this happens. I want you to watch the capacitor and the inductor voltage. So I want you to watch these two voltages up here at the top, and I want you to watch what happens at high and low frequencies, okay? So let's go to low frequencies. Look at that. The capacitor is big and everything else is small. Agreed? What if we go to high frequencies? The inductor is big and everything else is small. It turns out a capacitor and an inductor, they do not behave the same as a resistor, but we can think of them as impeding current flow. We can think of them as trying to slow down the amount or trying to reduce the amount of current. Over here on the right side of this thing, or I don't know what side that is on Zoom land or your land, I want to point out, look at these weird equations right here. There's an equation that says X subscript C is equal to 1 over omega C. There's also one that says X subscript L is equal to omega L. These things are called reactances. They're not resistances. One of them is called the inductive reactance. The other is the capacitive reactance. If you're wondering where this is, it's somewhere on 200, about 6 lines down. Okay, these equations are written for you there. Notice the units. You might be saying, how do they get ohms out of this? I'll remind you, do you remember the time constant for RC transients? It's just RC, right? So seconds, ohms, and capacitance all relate. This is the same relationship right here, right? Somehow seconds, ohms, because this omega is 1 over seconds or radians per second. So, okay, there's some ohms in there somewhere. So basically, and notice the time constant for RL transients was like L over R, I believe. So there's seconds and ohms, all these things are related. Okay, but notice the following. The capacitor impedes current flow at low frequencies, right? You get a lot of capacitor ohms at low frequencies because it's 1 over omega, and you get a lot of inductor ohms at high frequencies. So nobody calls them inductor ohms and capacitor ohms, but they're called reactances. They're in units of ohms. So, all right, let's just check this one more time. Watch those numbers, XC and XL, as I sweep the frequency. As I go down, somewhere right here in the middle, look at that. There's one special value where they're equal to each other. Interesting. Then as I go to lower and lower frequencies, we see that at low frequencies, the capacitor is dominating things. By that, I mean it has the most ohms by far. And when I crank this up, whoops, way high, the inductor is dominating. It's got the most ohms. Everybody okay with that? All right, seems reasonable. All right. Zoomers, are you doing all right with that? Any questions right now?
So far, so good.
Okay. Let me get my eraser. So, all right, so we've learned a little bit here. All right, now I want to talk about the capacitor and the inductor again. Let's look at these guys up at top. In particular, this is what's kind of interesting. Look at the peaking. Which one's peaking first? The inductor, the green one, or the capacitor? They're completely opposite. Do you agree? Depending on your point of view, you could say, oh, one's peaking while the other's at a trough. Well, then half a cycle later, it flips. This is very interesting. Look at this. If you're exactly at resonance, oops, if I'm at this special frequency, oops, sorry. Oh my gosh, come on now. There. Sorry about that. If you're at this one special frequency, do you agree they're exactly the same height? They're both 34, about 35 volts RMS. So, right, their amplitude relates to 35 and square root of 2. But one's out of phase with the other. By that, I mean one's at the top while the other's at the bottom. Look at the resistor voltage right now at resonance. Recognize that number? This is what's so crazy. If you're at the one special frequency, the LC together act a lot like that oscillator from last time. They conserve energy. They don't use any of the power supply's energy. They make it these crazy high values, but the resistor is given full source power. The resistor gets all of the source voltage. Do you see that? So this is what's special about these types of circuits. The inductor and the capacitor could have these crazy voltages. If you're too low, the capacitor blocks the current. If you're too high, the inductor blocks the current, right? And so if the porridge is just right, if you have this one special frequency, gosh, this again. If we're at this one special frequency, the resistor gets the full power of the source. Okay? Take a guess what that resonance frequency is. Does anybody remember from last time? What was omega naught for the LC oscillator? 1 over square root of LC. Now, we can derive this later, but if you set these two equations on the right side, the XC and the XL, the reactances, if you set them equal, I don't know if you can see that omega is going to equal the square root of LC. So when the two when the capacitor ohms and the inductor ohms equal each other, it turns out omega naught, or omega happens to equal 1 over square root of LC again. All right, still doing all right? Okay, I'm trying to get through this as quickly as I can. One of the things that you're going to hear about in your textbook that's very difficult to understand is these spinning arrows. Do you see the spinning arrows in the upper right? Let me get some eraser here, clear up some of this junk. And anytime, if you guys have any questions, ask away. But all right, can I put this on the side? All right, let's just go here. I want to talk about this part here, the spinning arrows. You can think of, this is a very interesting thing. It's in a lot of branches of optics and different branches of science. These things are called phasors. Maybe you've heard of a phasor before. Probably you heard of a phasor if you took 162. If you didn't, you have no clue, right? But the idea is, what is a phasor? A phasor is supposed to be one of these vectors spinning around in a circle at a certain rate. Notice that the sine waves and cosine waves correspond to the tip of that arrow as it spins. Do you see that? So it turns out you can write down these phasors in complex number theory, because you can think of this grid as being the complex number plane, where this is the real axis and this is the imaginary axis. And if you're passionate about that, I will go into it later. But for right now, I just want you to think of it as a spinning arrow tracing out these waves. And notice the arrows do not all point the same way. If you're wondering why they don't point the same way, I'm going to remind you of some equations. V equals IR for a resistor, right? Does anybody remember the equation for capacitors? Q equals VC. C dV dt. So notice that the current is related to a derivative of a velocity. Now just hear me out really quick. Do you agree that like current is some kind of sine wave? Well, then a derivative or an integral is going to give you a cosine somehow, possibly with a minus sign. So the idea is if the resistor is in phase with the current, the capacitor is 90 degrees out of phase with it. It's going to look like, so if the current looks like a sine wave, the capacitor voltage should look like a cosine wave. Similarly, what was our equation for the inductor? Do you remember? V sub L equals
Negative L di dt.
negative L di dt. Do you see there's another one of these derivatives here? But there's a minus sign in here. The idea here is, okay, if the current is a sine wave, the voltage on the inductor should probably be a cosine wave. And notice it should be flipped from the capacitor, right? There's a minus sign in there. So the idea is you can imagine, and then I'm totally glossing over a lot here, but the idea is it actually makes sense that these waves are all peaking at different times. Look at the resistor peaking at a different time than the capacitor, at a different time than the inductor. That's what we're trying to see with this. Notice the arrows are all spinning around at the same omega. They're all spinning at the same rate, but they all peak at different times. Good with that? All right, all right. Let me see. I think we've got a couple more pieces here. And I hope this is, and we're going to do math on this later. So I'm trying to give you the concepts now. Like I said, you can watch that SBCC video if you hate my presentation. But I'm trying to give you a conceptual view of this all at once. All right, let me get rid of some crap here. Whoops. Let's bring that back. There's nothing wrong with having that there. But I do want to get rid of this stuff. So I don't spend that much time on the phasors now that we've discussed that. I want you to look at another thing here. I want to talk about this right here. Z versus frequency. Now, frequency is the letter F. But I hope you agree the letter F is a lot like the symbol omega, right? Frequency, omega are related. 2 pi F is omega. Now, Z to the -1, you don't really need to understand that yet, or what this symbol Z is. I will get to that. But for right now, I just want to point out, this is I max. Can anybody tell me what I max is? What the word, like give me a word definition of I max from last class. Current amplitude. That was the current amplitude, right? Do you agree that's the amplitude of this? Watch it. The idea is I'm going to sweep the frequency and the current amplitude should change. Well, we saw this already, right? Watch it. Watch that plot now. Okay, I should be careful. There's a lot of plots. Watch this plot while I change the frequency. Okay. The idea is Z to the -1 is their way of saying current amplitude. You see the current amplitude getting bigger, and right at this one special thing, this one special frequency, we call this resonance. We get the largest current when the capacitor and the inductor are perfectly balanced and all the power goes to the resistor. Cool? So, almost there. One last piece. Is this helping your understanding of this picture or not? Do you feel like you're getting some of it? You don't really learn until you make the plots yourself, but okay. Finally, I want to talk about phase angles. We alluded to this last time. I want to look at, oh, whoops. Let me, sorry, let's get this here, get this here, get this here. Right. And I want to talk about this triangle that you see. See it flashing back and forth? in this case, I want to have some room here. What could I do? I know what to do. Notice it keeps changing on you, and there's no pause button here to lock that. So what I'm going to do is actually scroll down, and hopefully this will work. I've got some space down here. I'm going to draw this triangle, and then we can go back up and look at the circuit. We saw that there's this thing here. There was a triangle that looked like this, and we're claiming there's this thing called the phase angle. There's a resistance here, and there's this symbol Z, which we haven't explained yet. And then there was XL minus XC. Now keep in mind, this is something like the ohms from the cap and the inductor, right? We're taking the difference of the capacitor and the inductor ohms. Over here we have the resistance. The idea is if you know the frequency, you could figure out this. These are the equations that we saw right over here. And we're going to work this out and do an example. If you know the frequency and the capacitance and the inductance, we could figure out this side of the triangle. If you know the resistance, you can figure out this side of the triangle. So if we know the inductance and capacitance and omega, we get that side. We know the resistance. Notice you could get what's called the phase angle. This symbol Z is called total impedance. It's the total amount of ohms in the circuit. And it comes from those triangles, right? Some things are peaking at different times. I don't know if you noticed, some of them are peaking first and some of them are peaking second. But we can actually use this information to get the phase angle. All right, so that triangle helps us understand this. Let me get rid of that and go back up and show you these peaks. Sorry, I got to do it this way. I promise we're getting close to board work. Right? So the idea is, why are we writing XL minus XC? Well, it's because when the inductor is up, the capacitor is down. Look at these two curves or these two arrows, right? When the capacitor is up, the inductor is down. So that's where the XL minus XC comes from. At right angles to it is the resistance, right? And so the idea is if we know these parameters, we can learn about the phase angle. And it turns out, if you are curious, the I max, we used to say I max was equal to voltage over resistance. Now it's going to be V naught, the source amplitude, over this new quantity Z, the total amount of ohms. So instead of Ohm's law being V naught equals IR, now it's going to be Ohm's law for the amplitudes is V naught equals IZ. Woo, that's a lot. That's our, I don't know. In theory, that's everything here. And then the idea is it gets very complicated if I just change one piece of this. I don't know. Am I putting you guys to sleep? It looks like I should probably, okay. Yeah. I'm ready to do some board work if you are. I feel like we've kind of got an introduction, right? Any questions before we do that from people in the room or from Zoom? All right, all right. That's our conceptual theory. That's a lot. If you don't understand this, watch that SBCC lecture again after this, or watch this lecture again. Oh, there's a chat question. Oh, okay. I don't know. Great. Somehow I've got a, there's a bot that's streaming or that's trying to make X-rated things in the live stream. I don't know how to turn this off. This is great.
I guess you can do it later. It's not a big deal.
Yeah, I don't know how to do this, right? So whatever. I didn't even notice. You can tell. Yeah. Thanks for letting me know, Jacob. I didn't know how that, I don't know how that works at all. All right, so let's just not worry about it and hope it goes away. That's always a great solution. All right, yeah. Okay. All right, so let's get out of here. All right, thank you for putting up with that. I know it's late in the day and it's clearly tough for you guys to stay focused on that. Trying to go slow because it's so confusing, but slow with the lights off is never good. So, oh, yeah. All right. All right. Okay. Let's do a workbook problem together. 31.3, and try and see how this relates to paper and pencil calculations. I hope that'll help you stay awake. And let me see, I gotta remember to do this. I gotta remember to do that. Okay, 31.3. Maybe. What? I do want to show you something. Look at this. I brought this stupid thing. Let's do it. My claim is this is exactly the same as what you were just looking at. A lot of times students see this stuff and they're like, man, I'm not going to be an electrical engineer. I don't care about this. But I'm going to try and make you see, in my opinion. Okay, all this is a bunch of tennis balls on these brass rods, and I can shake this thing, right? Now, I want to point out, I want you to think of each one of these as a different circuit. Do you agree that if you change the inductor and the capacitor, you change the resonant frequency of a circuit, right? Think about this. Mass is like inductance. These all have the same mass. They're all a tennis ball, but the spring constant has to do with the stiffness of this, kind of like this inverted pendulum here, right? And so you could think about the length of this as being like the capacitance, okay? Because the length of it adjusts the springiness. Now I'm just going to check this one. 1, 2. Okay, the idea is I'm now going to be the voltage source. I'm going to shake this thing. And the idea is, notice, I get this violent oscillation. I get a lot of motion when I apply the right frequency. This one hit resonance. This one had max current, maximum velocity, right? Now look at this one. The idea is they're all connected, but only the one that has the right resonance frequency will get the most current. So the idea is if you apply the right source voltage, or excuse me, the right source frequency, you can get a lot of current, but it's going to depend on your mass or your inductance and your spring constant or your capacitance. So far, so good? That's really what we're trying to understand when we do this math. Believe it or not, this shows up everywhere in mechanical engineering, civil engineering, chemical engineering, chemistry, you name it, it's there. So, okay, enough said on this. All that for this. Okay, now let's do 31.3. Apologies there. I think that's kind of fun though, right? Yeah. A little bit more fun than that, just all math all the time. Okay. We've got an AC source. Don't draw a battery anymore. Draw something that looks like a sine wave inside of a circle. Okay, it's an AC source. That's supposed to be a sine wave. You can draw it any way you want. It doesn't matter on the order, but I'm going to try and draw it this way. I like to put my resistor at the bottom because when we do this in lab, that's going to be useful. So just if you have the choice to order the components, maybe consider doing L, C, and R at the bottom for grounding issues that I don't want to explain now. I believe this was 3.00 millihenries. This was 20.0 microfarads. And this was 1.00 kilo. Now, the voltage of the source, it's not a battery, so it's not just E anymore. Do you agree it's going to be V as a function of time? And we're saying it's some value V0 sine of omega t. The claim in the workbook problem is that omega equals the operating angular frequency. Sometimes you'll see me write this omega operating. That was like the frequency I was shaking the tennis balls. That's right. The tennis balls had a resonance frequency, right? But that doesn't mean I shook it at the right resonant frequency. Omega means the frequency I shake it at, not necessarily the frequency it likes to be shaken at. All right. Was that 9.549?
Yes.
Thank you. Radians per second?
Yes, sir.
Okay. And then what else did we know? What does V naught mean again? Can you remind me? Source, voltage, amplitude. It is not the voltage of the source. The voltage of the source is the entire sine wave. V naught is just the amplitude of that sine wave. I cannot stress that enough. It's very easy to confuse these terms. So V naught was, is this 100 in this problem?
Yes.
Okay. All right. Did they tell us anything else in this problem? Any other data that we know? I think that's it, right? Okay. All right. All right. Let's go on and do part A. What is part A? Resonant frequency?
Yeah.
What am I looking for?
Omega naught.
I want F naught. Now, to be clear, omega naught is the thing that we know the equation for. That's the resonance angular frequency, right? What's the equation for the resonance angular frequency? 1 over the square root of LC. And F naught, do you remember how I get F naught from omega naught? 2 pi over omega naught. Excellent. Now, we don't usually do this, but just let's plug in the numbers and make sure you're fast. I don't know if you remember me telling you last time that even I like to use numbers for these problems on test day. And I'm a physicist, right? Physicists never like to use numbers. But sometimes there's a lot to be learned. In particular, I want you to be fast with the EE button, so let's practice. So I got 1 divided by square root of, what was L? 3E negative 3, right? So you could use this as E negative 3. And remember, the prefixes are on the back of your book if you forgot them. Times, what was it? 20 E negative 6. 4082? Yep. Now, in this case, how many sig figs should I keep?
3.
4. 3 is appropriate if this was my final answer, but I may be using this for others. Do you agree, Jacob?
Oh yeah.
So if the question on the test was to get that number, yeah. But since I'm going to be using it later, it's important to keep the extra sig figs. So then I'm going to do 2 pi div answer. Whoops. Did I screw up there? It was 2 pi. Let me double check. Omega naught equals 2 pi f. Oh, I did screw up, didn't I? What did I do wrong here? I flipped it. Do you agree? I'm a bad person. I'm a bad person. That's why I should, this is what I have memorized. And this is what happens, right? I've been doing this 20 years, 30 years. And I put this in my head, and then the one time I don't write anything down, I screw up. Keep that in mind. The same will happen to you. Okay, so I screwed it up. 4082. Whoops, let's just go up here. Oh, jeez. This divided by 2 divided by pi, right? 649.7. What are the units? It hurts. So on your test, you'd probably write 650, right? Okay. That's part A. What's part B? What is it? Phase angle. So do you remember how we got the phase angle? What did I recommend to do? Triangle. Excellent. And you may not remember this triangle, so I'll help you get it. We know that R is on this side. This side was XL minus XC. This was the phase angle, and this side was Z. Okay, now again, you don't really know this stuff yet. Let's just kind of go through the math, and then we can talk about the meaning. Well, first up, I need XL, right? What was the equation for that? Omega L. All right. Let's see what we get there. Omega was what? 4082, right? Yeah, nice, Niles. This is omega naught, right? This is the special frequency. That's not the frequency, right? See the difference? This is the frequency that I'm shaking those tennis balls at, right? So that's the frequency that tells me how many ohms I get for the inductor. So it's 9.549 times, what was it, 3e minus 3? So I got 0.2865. Or you could say it's, what is that, 28.65 milliohms. And then, right, the sig fig is just to say we should be rounding to 3. In this case, maybe I'll include the 4.7 here. Turns out this term doesn't matter at all. Look at this. This is milliohms. Compare that to a kilo ohm. Do you agree this is nothing? It's almost what, 10,000, 100,000 times smaller. So that this inductor doesn't matter at all. What about XC? 1 over. I'm going to say, what is that? 5,236? Let's double check. We'll see if my memory works from earlier today. It's only because I have it memorized from the first class, not because I could do that in my head. Is that what you got? Okay. Now, when you look at this picture, how would you get the phase angle if you were doing trig? Tan inverse. Arctan of what? Now notice here, which term is going to be bigger for this circuit, XL or XC? So really what's going to happen here, do you agree that would be like having a negative height triangle? That's the same thing as drawing the triangle upside down, so to speak. So I don't want you to get too weirded out. It's okay to get a negative height here. That just means the triangle's really upside down, okay? All right, so in this case, we're also going to get a negative angle. Agreed? Let's punch it in. What do you get? So do you agree the inductor basically doesn't matter at all compared to 5,000? But you can put it in there if you care. 0.0286 minus 5236. Divide that by, the resistor was how much? 1,000. Then we'll do, what is it, tan inverse of the answer? Negative 79.19 degrees. Remember, phase angles we usually write in degrees. Everybody good with that? And then, do you agree that sometime we might need to plug this in, so maybe we should also get it in radians? How do I get this number in radians? Yeah, okay, exactly. So I'm going to multiply by pi and divide by 180. So it should be negative 1.382 radians. Just in case we need it. It's always good to remember that. Anybody else forget what we're supposed to be doing? Hey, we got it. Sweet. I was just about to read. I totally forgot. So far, so good? Is this kind of helping you understand the equations a little bit? All right, let's see what we're getting here for part C. What is next? Impedance. I don't know if you know what this means. That's the symbol Z. So Z means total impedance. How do you think we do that? And how do you
Use the
spell it?
triangle.
I gotta read how to spell it. There we go. Just making sure. I'm always like worried it's an ENC or something, right? Yeah. Do you agree that's gonna be the square root of what?
R squared.
R squared.
XL. C. Squared.
Yeah, I would say XL minus XC quantity squared, but yeah, I know what you mean. This part of the triangle squared. I'm gonna go out on a limb and say that's 5,331. I don't know why.
Squared.
Double check. That makes sense because it should be only a little bit bigger than this, right? So double check. 5236 x squared plus 1,000, right? So you have to kind of always be looking at your prefixes. This is why I really like this problem, because you're constantly having to think about prefixes. And we got to square root that. Yeah, that's pretty close, right? Certainly to 3 sig figs, that's good. All right. So far, so good. Now, this is what I want you to, this is an important thing. These two pieces. So take a second, even if you're tired, to think about what this means. The phase angle tells you whether the current is leading or lagging. This is going to tell us, and I'll go over how you can understand this. This has to do with whether it's peaking or which one's peaking first, the current or the voltage, okay? Remember we saw that earlier? This one talks about the total number of ohms in the circuit. So this is what determines the current amplitude. Remember I said that? So if you recall, the current amplitude, and I don't want to say the current, I want to say the current amplitude, which was the symbol I max, was equal to source amplitude divided by ohms. So it's equal to V naught, the source voltage amplitude, divided by total amount of ohms. Got it? But nobody speaks like that. They'd say current amplitude is source amplitude divided by total impedance. Nobody says total amount of ohms, but it helps us to think when we're first learning that way. What do we get for that? 1876 milliamps? I hope so. So,
Yeah.
is that it? All right, man. I don't have to feel bad if I eat that extra gummy tonight. I'll say like, oh, see, my brain still works. By that, I meant a multivitamin. Okay. There we go. Got it? I don't even know if we needed that, but I'm pretty sure we need it for the next step.
Yeah, we're certified C.
Yeah, so so this is why you care about Z, because usually you care about how much current you have in a circuit, because current is what does work for you. We'll discover that in the next part, I believe. What's the next part? Power. All right, look through page 200. Do you see any equations for power there? Maybe it's not there. Look on your equation sheet for the exam. Look on the very back. That's right. The current is what oops, sorry, too much going on. Okay, here's the idea. Remember in this circuit, we have an inductor, a capacitor, and a resistor. I want you to think of the inductor as magnetic energy. That's conservative. The capacitor as electrical energy, also conservative. The resistor gets hot and wastes energy. So the power relates to the resistance. So you probably remember power equals IV, right? That's not quite true anymore. The voltage here and the current have this weird issue where they don't peak at the same time, right? There's an issue with when they start and stop. So it turns out we have to put in a cosine of the phase angle. This relates to, and this is on your exam equation sheet. It might not be on, it's somewhere down there near the bottom on the far left. Right here. See it? But notice there's these extra terms here. Average, let me make this stand out. Right? The power is complicated because it's constantly going up and down, and shifting all over. So we say the average power relates to the RMS current and the RMS voltage and the phase angle. I don't like this equation. I actually prefer this other one, which I'm going to show you. This equation is still valid because it's entirely based on current and resistance. So if we talk about current and voltage, we have to account for the phase angle somehow. But remember, because the inductor and the capacitor conserve energy, it's only the resistor that's burning up power. So if we talk about the current only, then we can still use I squared R. And this is why I really like this equation. That's how I remember power instead of IV sometimes. Is everybody okay with that? But then, help me out. I know your brain is completely full, you're tired, you want to quit. Do you remember how RMS related to any of this other crap? Do you remember how RMS, in particular, how IRMS relates to Imax? The square root of 2. Oh, that's great. If you want to know why this is true, I'm going to sketch it out really briefly. All you have to do is memorize this result, and I think this is on your equation sheet. Double check. I don't know if it is. Okay, you better memorize that.
RMS.
Where is it? Oh, yeah. There it is. There's the relationship right there. Thank you. Right there. Thank you. All right. I want you to think about something. What does RMS stand for? Root mean square. It's not a nice square. It's a mean square. Okay. Now think about this. The current is some kind of sine wave, right? Well, when we talk about root mean square, I want to think about it actually as square mean root. I want to do them in the backwards operation. So what's going to happen when I square these? Oh, whoops, I need a little more space. So if this is I as a function of time, wouldn't I squared be all positive like this? Does that make sense? Now we did the square, take the average of that. You guys probably about halfway. Turns out exactly halfway. If you don't understand the math, I'll show you later. But it turns out to be exactly halfway. Now if you take the square root of exactly halfway gives you this square root of 2. Okay? If you really are passionate about needing to understand this and you don't want to, I discussed the actual math of it on problem 31.9, page 203. So if you're passionate about that, it's there for you. That's the strict mathematical way to show VRMS. For now, we just got to learn one thing at a time. Okay? So if you are passionate about understanding RMS, talk to me later. Okay? Now I need space. All right. Great. Well, do we have all the pieces we need to do this now? I think we do, because we know Imax was 18.76 milliamps. I can divide that by root 2, but actually maybe I'll just plug it in first before I do that, right? Because then it's easier. I only get a 2. Do you agree that the power on average, I hope I'm on the right whiteboard for Zoom. Yes. Do you agree that's going to be I max squared over 2, because I get a √2 and then a √2 when I square it. And then there's an R. Let's crank that out. Imax was 1876, or 100 divided by that last number. And I'm going to square that, divide by 2, and then times by 1,000, because R was 1,000. I got 176 milliwatts. What are the units there? Is that right? Did I do the rounding right? All right. And yeah, I'm kind of getting lazy with the sig figs, but we're getting towards the end of the problem, so it's okay. There's less probability of intermediate rounding error. So, okay, so there's the average power. Cool? All right. What's next? Plot it. All right. And I think, I'm looking at the time. Do you agree it's almost 6 o'clock here?
Yeah.
I think what we should do is take a 10-minute break. And when we come back, I brought the laptops. I want you to actually take the time and do this with me on the laptops. I think it'll help you stay awake. I think it'll help you be faster in lab next week. And I think there's something you can learn from actually playing with it. And then once you have this, you can take the file with you and then mess with it afterwards. Okay? Let's take our break now. And then Zoomers, we're going to be doing Excel when we come back. And I'll see if I can figure out this weird spam bot.
Hey, Jorstad.
Oh,
So, so for 31.3, part D says, determine power delivered to the resistor at this operating frequency. Why is that average
say
power?
average power, did I? I screwed
No.
up. Let's do one more thing here. He's right. I screwed up.
I was just, yeah, I was a little.
Oh, no, you're right. And in the solutions, I remember to take, I wasn't reading carefully. Do you agree it doesn't say average power in the problem? So, well, I showed you how to get the average power. That's usually what people mean. But power instantaneous would be I as a function of time squared times R. Well, how do I get I as a function of time? The general solution, or page 200. It's going to be I max. Thank you. Thanks, Jake. This is where the phase angle comes in. So I think we know all these numbers. Do you agree we know this number, I max? That was 1876 milliamps. What was omega? 4082? No. Omega naught is 4082. Gotcha. This is the omega operating. You're going to hear me do this to you every single problem. Okay. What was phi? What was the name of this thing? Phi? Phase angle. And we figured that out somewhere, didn't we? And here's the thing. Everybody says negative 79.2 degrees, I think is what we found. But when you plug it in here, do you agree we're going to have everything in the same units? And we're going to do it in Excel because nobody wants to plot this for real. So that means we're going to have to do everything in radians. That's what we'll do when we come back. Jacob, do you feel good on that?
Yeah, thanks. I was just curious how the text of that would imply average, but all good now.
It didn't. Now, to be honest, on exam day and for both midterm 3 and the final, I generally, I can't remember if I've ever, even once in my life, ever asked for the instantaneous power. Usually the only thing anyone really cares about is average power. But you can see here, we have to be very, very careful with the way we speak to each other and make sure we're understanding. So don't be shy on exam 3 if you're doing this. Say, did you mean average power? And I'll be like, yes, it says average power right there. I hope. All right, now let's take our break. Okay, sorry about that. And thank you so much for pointing that out. Oh my goodness. Good call, Jacob. Good call. here. And then we'll go to right here. I need to get a Excel spreadsheet open, okay? And so I know that maybe this isn't, I don't know. I feel this is a good idea to do this. Now, what I want to do is I want to not care about formatting. Is everybody okay with that? So normally I'm like super carried about formatting because it's the right thing to do. But so for this one, oh, did I click screen share on Zoom yet?
Hey, Jorsted.
Oh,
Before we move on, can I just continue with part D real quick?
yeah,
So we were, because we don't have time, right? We were gonna leave it as a function, right? And plug
that's
everything else
right.
in,
We
basically.
found that, yeah, so it was as a function of time, t is some variable, yes.
Okay, got it. Thanks.
Cool. All right. And then the reason I'm bringing up a spreadsheet now is because we can make a column of data for t and analyze it,
Right, okay.
right? So now I'm not going to put the units on all of these here, but this is what I want to do. Have your workbook handy so you can get your numbers ready. All right. And then, you know, I seriously think we can learn something from this. Otherwise, I wouldn't be wasting my time. So let's write down R in the units given. Now I'm going to say KW. There's a few of these. I'm going to actually change the symbol font. So I do want to show you this one thing just because the units probably are going to help us understand this problem. So W in the symbol font, if you just type SYM and enter, that's our ohms, right? Now, I'm not going to worry about italics and stuff like that. So it was 1, right? All right. And I like to have all my stuff centered like that. So I'm just going to do that really quick. Again, I just click the all and then just mess around and center your data. Okay. What was L? Was it millihenries?
Yeah.
And what was it? 3.00?
Yeah.
All right. Can you see okay in the back? Julie, you're good? All right. And then what was C? Microfarads. So I can highlight that M, change it to symbol font, SYM, enter. It was 20.0.
Yeah.
All right. Now, in this case, what was V naught, right? So I'm just going to do V naught in volts. That was 100, I think. And then omega, that's W, lowercase, right? So I'm going to, again, just because I do want to use the Greek letters right for reasons, we'll do that. What was it, 9.549? Yes, radians per second. So those were all the givens in this problem, right? Is that too small in the back? Maybe I'll make it a little bigger. Does that help? Yeah, all right. Sorry about that. Zoom, can you see all right?
Yep.
Okay, so now one of the things that I like to do is I like to make a second row without any prefixes. So what I'm going to do is just highlight these column headings. Right? And let's just get rid of the kilo, get rid of the milli, get rid of the micro, and I guess that's the only ones we need to do, right? So this would equal that resistance, what, times 1,000 times 1E3, kilo is 1E3. The inductance would be times 1E negative 3, 1E negative 3. Am I going too fast or is this approximately okay? Okay. At any time, anyone on Zoom or here just say, whoops, I didn't see how you got cell, blah, blah, blah. So if you didn't see how I got cell C5, just say, how'd you get C5? Okay. All right. Now let's kind of go through the same steps that we did before. Wasn't there a resonance frequency? How did we get the resonance frequency? Do you remember? Let me do this. Okay.
Yeah.
I like what you're saying. When I said resonance frequency, I meant angular resonance frequency. And we're all going to do this at some point. So I should have said, how do you get omega naught?
Oh. 1 over squared LC.
which LC should I use? The ones with the prefixes or the ones without? To do it. There we go. And then I'll get rid of some of those sig figs because they drive me nuts. And then you were saying F naught in hertz was what? 1 over, or wait, it was omega naught over 2 pi, wasn't it?
Yeah.
Divided by 2, divided by, check this out. When you divide by pi, I put the parentheses too. Right? 650, that's what we found before. All right. And then maybe we should make another column here. How about X subscript L? Didn't we have to figure that out? And that was in ohms, wasn't it? Right, so what was that in ohms? How did we get that?
Omega times
Which cell should I type?
the E2,
E2, good, good. Times which other one?
the E5.
B5, right? Because that's the right omega and the right L with the units. So there's a little subtlety when you're doing this in Excel, right? And then XC, and if you want to race ahead, I'm totally cool with that. Yeah, am I going too slow?
A little fast.
Oh, shit, my bad. Okay, I'll slow down.
What do you prefer? Omega naught with equation?
Okay, yeah. Do you agree that omega naught, so I'm going to go back to D5. Omega naught was 1 over the square root of LC, and I had to get the right L and the right C, the ones without the prefixes on it. Is that helping?
I see the L. But without the people.
So the L without the, so remember, these were the ones, the reason I wrote that first line was that's what they gave me in the problem. I don't want to screw up. So I write down exactly what the problem gives me. Then this one is my conversions. Did I address your question or did I not understand your question?
Yeah, but is L to get that what I get E2 times 10E negative 3.
Right here, how did I get this? Oh, equals this one, milli. That's 1E negative 3. Milli is negative 3. So it's always 1E prefix number. Got it? Okay. And then after you do that, it makes it look different. But do you agree that you could have also gotten that just B2 divided by 1,000? But yeah, what I find is I've got all the prefix numbers on my workbook, right? So rather than try and constantly remember, do I multiply, divide by, right? Just say always multiply by 1E prefix number. And then it always works. Yeah. All right. Is everybody okay with omega naught? How about F naught? That was omega naught divided by 2 pi. That's what we found before. Remember that?
Yes.
Is everybody okay with that? And then you can't just type divide by pi. I think if you just type divide by pi, it doesn't work. Or does it auto put in the front? Yeah, see, it says name. So pi is a function. And I vaguely recall, maybe I'm wrong, but I thought if you like put a number inside, that tells you how many digits of pi. But I could be wrong. You could read the help file. I really don't care. I'm going to use max digits. So is that okay with, whoops, F naught? Everybody okay with that? What's that? So here's the trick. Look, see where, do you see where I'm highlighting up in the fraction bar or the function bar? That's how I got it. So, whoops, I just screwed up. Let me just do it again. It's equal to omega naught, which is D5, divided by 2 pi. So when I divide by 2 pi, you either have to remember the parentheses or I just divide by the first number, then divide again by the second number. That's the same thing as dividing by 2 pi in parentheses. One of the more common mistakes everybody makes on a test is they'll divide by 2 pi in their calculator, forget the parentheses, and basically be off by a factor of 10.
I just had that.
Did you have that?
Yeah.
Yeah, that's like the most, it's seriously one of the most, and then I don't want to think about this. This is usually one of the first things in the problem. So if you screw that up, all your work, and then it takes forever to grade. So it's like, oh man, so hopefully you don't do that. I try to give you some partial credit if that's your only mistake, but it's pretty time consuming. All right. XL, is everybody okay with XL? That's the inductive reactance. If you don't know where I got that from, I've got the formulas on page 200 kind of sitting out in front of me here, right? Okay, and now XC equals 1 divided by E2 divided by C5. That way I don't need any parentheses. It's easier for me to read. There we go. All right, now we've got those. Why don't we make a column for Z? Do you remember that? Do you remember how we got Z? It was the triangle, and maybe I'll draw this here. Remember we had our triangle? Our triangle was phi. Is this showing up on screen, everybody?
Yeah.
Thank you. Remember there is our phase triangle? This is not on your exam equation sheet, but I'm going to guess that all of you, as soon as you get handed your test, to draw this because it's so darn useful. Does everybody know what I'm saying to you here? I didn't have room to squeeze it in there, so you got to write this on your test as soon as you get it. All right. Symbol. Okay, so how did I get Z from that triangle? Do you remember? Equals square root of what? R squared. Ooh, hey, check this out. Why don't we name some of this crap? Couldn't I name this resist for the resistor? Couldn't I name this one IND for inductor? How about this one I call cap? And notice I'm using the one without the prefix. This one I'm going to call it X subscript L. X subscript L. And then this one I'm going to call it X subscript C, right? You guys know what I'm doing there? Yeah. Using the name. And if you didn't see that, I could show you that again. But now this is going to be a little bit easier to write. Equals the square root of resist squared plus X subscript L minus X subscript C quantity squared, like that. And that's the answer we got before, 5331. Did I do that too fast? Is that good? So naming these variables can really help. What's another variable I may need to name? How about V naught? Let's call that V naught. V subscript 0. That's what, when I say V naught, I mean V subscript 0. How about omega? What's a good name for omega? How about omega? Now, there's two different omegas here, right? If you want, you could call this omega oper for omega operating, or you could just call it omega and don't put a subscript on it. And that's what I'm going to choose to do. So we have to just always be thinking, is there a subscript on my omega? All right. How do I get the phase angle? Any idea? What's the symbol for phase angle? That's F. And so I'm going to change that in the symbol font. Right? So that's the F, F, phi, phi, pho, phi. Now, does anybody know how we get that? How did we get that? What was the formula? Tan inverse. Yeah, what's the tan inverse in here?
A10.
A-tan, money. Okay. So we're going to take A-tan of what? Look at the picture I have drawn up in the upper right corner there. Look at the phase triangle picture. Yes, Efren, right on. So I got to do X subscript L minus X subscript C divided by resist, I think is what I called it. Now, I like putting some space in just so I can see stuff, but you don't have to. Is everybody okay with that? When I hit this, do you notice it gives me the answer in radians because it uses radians? All right. But usually we think in degrees, right? So how can I convert that radians into degrees?
Equals degrees.
Whoa, degreasy. It sounds like like Calabrese Milanese torta or something, you know? Oh, man. Now I'm thinking about tortas. So if you type the degrees function, see how that spits it out for us? You could do the pi and the 180 crap, but who wants to do that? All right. So we're basically redoing everything we did, but this is how you would do it kind of as a professional, right? You would do it in a spreadsheet so that you could change everything. So it's a little bit different, but I hope you agree the numbers are all there. Okay, that was just to get us caught up. Now, didn't we also figure out Imax? What was Imax? V naught over Z. And that was going to be in, I think we did that one in milliamps, right? Well, let's just do it in amps. All right. We can always add another column. So it's equal to, what did I call it? V naught divided by Z. Oh, I didn't call it Z. Oh, okay. I better give that a name. I'm going to go over here and name this one impedance. How about impede? Imped, right? How about just, whatever. So this is equal to V naught divided by the impedance. That's amps. Okay. What if I want I max in milliamps? It's going to equal this divided by, whoops, times 1,000, right? All right. All right. So far, I hope I'm not wasting your time. We're almost ready to do what the question asked. All right. I'm going to call this one phi. You see the radians? Because we're doing calculations in Excel, this is the angle I want to call phi, the one that's in radians. Phi. All right. Now I'm ready. Almost. We want to make a plot of current and voltage versus time. Agreed? What was the question we were trying to do here at part E? Voltage and current versus time, right? Okay. So now we need a column of time in seconds. Do you agree? I know the first time I want 0. What is the next time interval? What interval should I use?
0.22.
Period and divide it.
Wait, say again, Jake.
Find the period and then
The
divide
period.
it by the frequency, I think.
Okay, so I want you to watch what I'm doing for a second and then tell me what I'm doing right or wrong. Period in seconds, right? Shouldn't that equal 2 times pi divided by the omega? Wrong omega. That's the resonant omega. You got it. So it should be 2 pi divided by E2, right?
Yeah.
Or what was it? Omega upper? Oh, I think I just called it omega, remember? That's our period. Why is that useful? If you want a smooth plot, what is your time increment supposed to be? Should it be
Period divided by 4.
No. Jacob, that would be the bare minimum, but that would not make it very smooth. If you want this to be a smooth plot, we might want to do a lot of points in one period, right? So
Yeah.
how about the period divided by 100 or something, right? Then each point would be 1/100th of the total cycle. You could pick a different number. You could pick 20 or something, but 100 should make a really smooth plot. So that is going to be, I would type this like this. I would call this dt up here. My time increment is dt, all right? So then I would say this cell should equal that cell plus the time increment. And so now you may be saying, why are you doing it this way, dude? I hate you. And that's true. But what will happen is all of our information is now referenced. If you change something, the time increment will change and we'll still see the plot. If you don't do it this way, right? Whoa. Something I did wrong there. I did it this way. There, I filled it down wrong. How far do we have to fill this down?
Oh, for one period?
For about one period, right? Which was 0.66. So let's just go until we hit 0.66. And then we'll always know we get a full period. Whoops. Normally this shows up, but. All right, how about right there? That's a full period, right? So 111 for me. Whoops. Okay, everybody okay with that? What's that? Or,
Oh, no,
okay, gotcha. We wanted to plot the source voltage in volts. Does anybody know the equation for source?
V naught sine omega t plus the phase angle.
No, it was V naught sine omega t without the phase angle. Different books you read may put the phase angle in the source voltage, but in this one, we're going to say this is the V source. Is just no phi. It was the current that had the phase angle. Do you remember that?
Oh, yeah, okay.
And that's just, to be honest, there's different ways. You'll see it in different books. All that matters is one of them has to have the phase angle because they're not peaking at the same time. Whoops, that's not right.
what's the subscript on the V source?
V source, that's supposed to be a V0, sorry. This right here. Thank you. Sorry about that. There. I was I max sine omega t minus phi. What does it say on page 200 there? About halfway down, it's minus phi. It's always important to think about your equations, and this stuff is written on the back of the test too. All right. That having those equations right there tells us, so this is equal to V naught times sine of omega, which was, I guess we just called it omega, right?
Yeah.
Times the time, which is what, A11? And we don't need to fill that down yet, right? We can now get the current. And I'm going to choose to do milliamps, okay? So here's where the units kind of matter. If I want the current in milliamps, now I would use the, did I call this thing Imax? I don't know if I did. I'm going to give it a name, Imax. Remember we've been calling it that all day? So I want to use the one that was in milliamps. You could choose which one you want. So it's Imax times sine, whoops, sine of omega times the time, which is cell A11, minus the phase angle in radians, which I think we called phi. I'll pause there. Is that helping? All right. Now we can fill this down. We don't need all those sig figs. I'm just going to grab both of them at once, fill it all the way down. And now I'm going to grab all three columns, fill it all, or bring it all the way up, not fill it. And I'm going to hit, whoops, insert plot. And then just to make this match, man, I've got too many annotations. I got to get rid of these annotations, I think, maybe. Or maybe I can just do this. There we go. So in this case, we're kind of getting there, right? Which thing is peaking first? The current or the voltage? Well, it's kind of hard to tell, but here's an old school trick. click on one of the curves. Do you agree that this blue curve must be the source voltage? Watch what happens when I click on the blue curve. In particular, watch right here. When I click on the blue curve, it tells me, whoops, I'm on the V. So now I can tell which one's which, right? This must be the source. So just so I can make this match up, I'm going to change this to red. Just so it matches. And then so Jesse could see, just in case, let's make it dashed. Whoops. Oops, come on now. There we go. And then these grid lines kind of drive me nuts, so let's get rid of those. Right, and now you can kind of see this thing a little bit. So the red dashed line is the current. And now we get to have a little fun with this. I'm going to make this small so I can see it and have everything else here. I'm going to get rid of this. The idea here is now, man, I got too much zoom going on here. All right, I need to put this somewhere. Did I go too fast or?
A little bit. I barely got caught up right now. So.
Okay. This explains why I always think the lab should take less time. I'm always like, ah, this is so fast, right? Just whip it together, right? Okay. Did you guys get it or questions or?
Oh, yeah.
Good? You're good? Good, good, good.
100%.
Check this out. Now that we spent all this damn time on it, we can do something really, really simple. What is going to happen if I increase the frequency? That's all I care about. So before I go on, Efren, you're good?
Yeah, I'm just having trouble naming them constant.
Oh, okay. So you want to see how to name a constant?
Yeah.
Watch what I do here. So let's say I want to name this one. See how it's E5 up here?
Yeah.
That's the name box. So you want to go up here and type in.
I know, I got that. But
Oh.
You know how you put like dollar signs?
Oh, so like if you want to do that, you could name a constant like this. Like let's say you said equals, let's say I wanted to use cell B5, right? If you hit F4
Yeah, that'll make it.
and just keep going back and forth, you can get the dollar signs in any pattern you want.
Okay.
And so for us, usually we use double dollar signs, $B, $5.
Doesn't matter which one we do.
Well, so if you do $B, $5, that locks both the row and the column.
Oh, okay.
So if you fill to the right or down, it's going to work.
So the dollar sign makes it.
This would only lock the row, which means as you, let's see, if you lock the row, I guess the column could change if you fill to the right. Whereas this locks only the column, so yeah, or something like that.
Okay, sweet.
And yes, there's times to use that, and we've used it when we made contour plots, if you recall,
Oh,
maybe. Yeah.
What did you use the labs for that?
Just so that the numbers would be approximately right. Think about this. The voltage can go back and forth between 100. The current is going to peak out at 0.0186. So if I plot them on the same plot, I'm not going to see the current. That's why I have to use the current in milliamps. Otherwise, it wouldn't show up.
Oh, so it doesn't affect the equation.
Right? Yeah. So like here, I could use this other one, but it would be so small, I wouldn't notice the phase angle.
Right.
Got it? Here's another thing. Look at your resistance in this. Do you agree it's all, in general, the resistance is going to be in the kilo ohm range? Kilo. So I always think about it like this. Kilo gives you milli. You're going to hear me say this in lab. If we've got kilo ohm resistors, usually you want to display milliamp currents. Okay, so kilo gives you milli. So that's how I remember. I like to use milliamps for my currents whenever I have kilo ohms for my resistors. I guess if you had mega gives you micro, but it doesn't kind of have the same range, right? Is that good?
Yeah.
All right, let's try something fun. Let's change the frequency. If I use double the frequency, before you change it, let's think. If I double the frequency, what do you think is going to happen? What will change? What won't? Take a second to kind of think it through, right? You can't see your equation, but just see if you kind of remember any of this crap. So let's walk through it. If I double the frequency, obviously none of these numbers are going to change. None of these numbers are gonna change. Will the resonance frequency change if I double the frequency? No.
Nope.
Resonance frequency depends on inductance and capacity, right? The frequency that I shake does not change the amount of brass and tennis ball, right? On that thing. Okay, so what about XL? Will
Yes.
that change?
Yes,
Yes. Should it go up or down?
if you want to, if you want to.
I'm gonna up the frequency. Let's say I change the frequency to 100, right? About 10 times bigger. What do you think is gonna happen to the inductance? 10 times bigger. What should happen to the capacitance?
10 times smaller.
Let's see. What else? What about Z? Will that change? Will it go up or down, do you think?
Stay the same?
No.
Nope, because it's gonna change with those, so.
That's gonna change with the XC.
Yeah, now think about it. XC is dominating right now. Do you agree? XC is so do you think it's gonna go up or down? What should happen to Z? It's gonna go down. XC is 5,000 right now, right? It's gonna go down to 500. This number is gonna be a lot closer to resistance. Okay, so let's do this. So, and then the phase angle, is that gonna change? If I use a lot bigger frequency, XL and XC change. Doesn't the phase angle depend on those?
Yes.
All right, now let's do it. Oh, what about the current? Is the current gonna change? If you have less ohms, we should have more current.
Oh, because that's with Z too, yep. Okay.
Yes, so let's change this up to 100 now. Look at that. See the big difference? You can now hit the undo button and just kind of compare and just see, undo back and forth. And just see, go ahead, take a second to look at your own screen and play with it. I'm gonna leave it this way. We got a lot more current. Does the period change? No. Does the phase angle change? It went from -79 to 26.6. Okay, that's a big difference. Let's try make the angular frequency 400. Oh my gosh, they're almost on top of each other. Do you see that? How did you do your time step? In particular, look in cell, for me, it's cell A12, the second time. Look how I did this. So notice I used a variable time step here. I said it equals A11 plus DT, and I made it calculate DT for me. I'm gonna pause and make sure you can see that. Is that helping, Jesse?
Let's see right now. I did it differently, so that's why I thought.
So the idea is you do not want to hard code the time step, right? The idea is you want to make the computer calculate the increment size for you. Is that what you didn't do?
I think so.
Because you're probably getting some aliasing. Do you get something that looks like this, Jesse?
Yeah.
And then it kind of gets small and it looks like FM radio?
Yes,
Yeah, so you didn't have the computer calculate your time step.
okay, so Chris, you're gonna have to redo your thing.
What's the special frequency I should use? What's the one special frequency in this whole damn thing? Resonance. Watch what happens when I type 4082. What do you notice about the current? Jesse can't notice anything because they're exactly on top of each other, Jess. That's a red and a blue line on top of each other.
Oh, no wonder.
You see nothing, right?
I just see the line.
Yeah. So, but the point is, compare the difference here. If I do 50, do you agree there's two lines?
Correct.
And then when I go to the resonance, do you agree there's only one line?
Yes.
That's literally because they're right on top of each other. Okay,
Can you go back to the time? The problems with mine.
this one?
The times per seconds, like, yeah, the DT and stuff like that.
Okay,
When me and Chris do it, we just get single numbers after that for some reason. I can just show you with that.
yeah.
So we did that, and then when you drag it down, it just goes to 1, 1, 2.
Oh, so let me see your A12. A12 is.
Oh, I need
Yeah,
to-
he's a constant on that.
Yeah, okay, let me
All right,
that's the reason
all
why.
right. Yeah, got it?
Yeah,
Yeah.
Okay.
That's the calculation for V source.
What's that?
For V source.
For V source? Whoops, hold on, let me escape out. Did you use dollar signs?
There's the calculation. So it's V sine omega t.
Yeah.
Oh, I see what happened.
By the way, if you're sitting out there thinking, oh man, we're gonna do example problems of this next week. I have another question for you. How many more lectures do we have
well, technically 2, and then.
total for the semester? 3.
What?
Yeah. Isn't that crazy?
Yeah.
Next week and the day before the final. We have an exam in there. And then the week of Thanksgiving, there's the optional extra credit activity, and then Youngblood's offering office hours on Sunday night for this class only. Because I have to give his finals for him, so he's gonna be offering. So believe it or not, we're doing fine on time. Look at this book. Right? We got 3 lectures. Look how much we've done. Look how much is left. And a lot of this is fluff, like stuff like, hey, if you're interested, study this. If you care, here's a bunch of words. We're almost there. Isn't that nutty? 3 more lectures with me and you never have to talk to me again. I hope. All right. For your sake, I enjoy talking to you, but most people don't like talking to me. All right. Okay, this is what I wanted to point out though, right? We started at 9.549, right? Our impedance is huge. Impedance is Z, right? What is the special value of impedance when we go to the resonant frequency? When I go to resonance, what do you get? R. Remember, the inductor and the capacitor balance out and you only have the resistor in the circuit, right? Right? If I go to resonant frequency, this has been running the whole day. If I go to resonant frequency, right, look at this over here. Right at resonance, we see these two have the same amount of ohms. They cancel out. XL minus XC equals 0. And then I get Z is equal to resistance. The phase angle goes to 0. Look at that phase angle. Check this out. There's like a few more conceptual things I need to stress here, and I'm going to discuss this. At 90, we get a negative phase angle. Z is bigger than R. What if I go to 9,000? I get a positive phase angle. Whoops, let's go to 90,000. I get a positive phase angle. Z is bigger than R. The minimum value of Z occurs at resonance because that's when XL and XC balance. Doing all right? Okay. Before I go to I want to do some board work now. I would save this file and maybe you could use it to help you generate the other files, right? You can change these things and plot them. Before I go to the board, are there any questions on this? Look at the phase. Oh, go ahead. Yeah.
Well, I was just gonna ask, is there anything special about omega being like a multiple of omega naught? Because I tried it and you get like a small positive, so I guess not, but.
No, right? I could just stick an extra 0 on here too, right? Yeah, I guess if you could, no, Jacob, there's nothing that I can think of right off.
All right.
Yeah, it's convenient though. All right, so I know you're tired. We got 10 minutes to go. Give me your attention one last time. Watch something special here. Watch the curves, right? Let's start out here at 9. Do you agree current is peaking first? Now let's go to 90. Current is still peaking first. Now let's go to 900. Current is basically peaking at the same time. The phase angle is close to 0. If we get right at there, 40, what was it? 82? Oops, 40, 80. They're basically right on top of each other. If we go to positive, larger frequencies, notice the voltage is peaking first. And we keep going. there's a phrase we're going to use to understand this, and I really want to make sure we cover that in the last 10 minutes. I need to go to the whiteboard. Is everybody ready for that?
Yeah.
All right, let's do it. Was that a worthwhile activity in your opinion or not? I feel like you'll be faster in lab and actually be able to learn something in lab rather than struggling on your own. So apologies if I wasted your time, but it seems like that was okay for most people there.
So
What do I need to do here? I need to turn the lights on. That's what I need to do. And I need to go to. Let's go to 5. All right. You can stand up, shake it off there, get loose. I want to explain something really quick. This to me is, I've been kind of dodging the phase angle question all night. But we've seen this over and over, and I've been dancing around it. It's time for us to get cold, ice cold.
I think you need to switch the board.
Oh, thank you.
Thanks.
And maybe I'll do it this way. What color have we been using for voltage?
great.
Good. Let's see if this other one works better. Nice, Jess. So we'll keep using gray.
Yep, sounds good to me.
I want to talk about Eli.
That's nice.
Oh, you will.
Eli the Musk.
That's what that.
And I'll let you choose tonight. Do we want to say Eli the Ice Man, Eli the Ice Organism, Eli the Ice Woman? What do you want? How about Eli the Ice Creature? Have we used that one?
Ice cube.
Ooh. He's jacking for beats. Eli the Ice Cube. I like that. That's fresh. Okay, now, this is a phrase you need to know, memorize, and just have it in the back of your head. This means if inductor dominates. That's what this phrase says to me, and it may not be obvious to you. If the inductor, how do I know that? L. If inductor dominates, well, when does the inductor dominate? At high frequencies or low frequencies? Do you remember? XL has to be bigger than XC. What was the equation for XL?
Omega L.
Omega L. What was the equation for XC?
1 over omega C.
So which, is this going to dominate at high frequencies or low frequencies? High. Remember that? At 9, it was like 0.02 or 2 millis.
Yeah.
At high frequencies, this thing gets big. At high frequencies. When we were at high frequencies, was that positive or negative phase angle?
Positive.
Remember, phi is equal to tangent inverse of what? Do you agree that if XL is bigger than XC, phi is positive?
Okay, that makes sense.
So I think all of these things when I see Eli. If I'm at a high frequency, now you may be saying high frequency, what is a high frequency? That's another way of saying omega is greater than omega naught. That's a high frequency. High frequency in some circuits might not be high frequency in the other circuit, right? It depends on this, the tennis ball type stuff. Okay, so if any of these things are true, the inductor dominates. If that's true, which thing peaks first, if you had to guess? Which comes first in the word? E peaks before current. Oh, let's just say voltage. And I'm going to say V source peaks before current. Remind me, what was the symbol for current? Was it I max? I max is not current. I max is
Current amplitude.
current amplitude. V source is not V0, right? To be clear, this is I as a function of time equals I max sine of omega t minus V. This one is V as a function of time equals V naught sine omega t, right? So the idea here is this sine wave will crest before that one. Sometimes you're going to hear it in the literature saying V source leads current. Okay. The other way you could say it is current lags the source. Are you okay with that? These words leading and lagging were super confusing to me when I was in your position learning this for the first time. Now, one of the reasons this section is hard for students is, do you agree all these symbols are somewhat interrelated? And what I discovered is, on test questions, I never really noticed this, but what will happen is I'll either say it this way or that way or that way or that way, and I assume students can interchange them just like I can. And what happened is, I think students will sometimes say the inductor dominates and they'd only know the first one. You have to know all of this cold to succeed on the test questions. Because sometimes I'll tell you the phase angle, I'm like, oh, the phase angle is negative. Of course they should have known ice, right? Here, oh, the phase angle is positive. They should have known Eli, right? The idea is I just assume once you know one piece, you know all the other pieces. If you know the phase angle is positive, you're supposed to immediately know you're at high frequency relative to resonance. You're supposed to know this too. All right, we ready to do ice? Okay, let's do ice cube. Now I've kind of run out of room, so I want to erase just this line here. Is that okay, or should I just do it on the other board?
Yeah.
Let's do it on the other board. Questions from Zoom? Is that okay?
All good.
All right. So I want you to kind of think what I'm going to say. On the next
Board
one.
didn't switch though. Sorry.
I know, I'm just erasing.
Oh, okay. Okay.
Yeah, I'll be there in just a sec, but thank you for checking. Not done yet. Okay. There we go. Okay. So ice. Ice. All right. Well, if I'm talking about ice, who's dominating? Cap dominates. By cap, I mean capacitor. The capacitor is going to dominate. What else would we know? XC is the big resistor, or the big amount of, I should be careful. It's not a resistor, it's a reactance, which is measured in ohms. What else? Is this high or low freak?
Low.
Yeah, that's low. Sorry, I'm just like paranoid because I want to make sure I get it right. Okay, I don't have a good aspect ratio, and so sometimes I'm more focused on markers than the words. Okay, so if we're below resonance frequency, what else? Does that make sense that phi should be less than 0? Let's write it out. I vaguely recall that I used chi back when I was in school, but now we just use x. The capital Greek letter that looks like x, but maybe I'm wrong. I don't know, like chi-square distribution. But so vaguely, but now I just use x. I don't care. So just be aware, maybe there's a different symbol used that looks like x, but it's a Greek letter. Is everybody cool that this implies a negative phase angle? The negative number is bigger when you punch in your calculator. All right. What else? So now the leading and lagging. Tell me a correct sentence with the words leading and lagging.
Current leads V source.
All right. Current leads V source.
Source lags current.
What do you think?
Dig it.
And so, all right. This will help. And so what I do is I kind of never use these terms because they're easy to screw up, right? So I just say ice. And I think other people might actually do that as well. So I tend to remember this, and then I don't really use these too much. I think I have asked a question on a test like, which of the following is true? Does current lead voltage or does voltage lead current? And I ask you to say, or sometimes at one time I did a true false question. True false, current leads voltage for this circuit. So every once in a while I will use these words. Look at the bottom of page 199. You see it in there? So you could play with these phase angles. By the way, at super low frequencies, why does the capacitor dominate? I know we're running late, but I think this helps. What's the lowest frequency you can imagine? 0. What happens to a capacitor at 0 frequency? If you put a battery on a capacitor, what happens? It charges up and blocks all current. It's an infinite resistor. Right? What about this inductor? If you're changing really frequently, the capacitor doesn't have time to charge up at all. It doesn't affect the circuit at all. But what is affected? An inductor. If you try to change the current, you're trying to change the flux too rapidly. It opposes changes in flux. And remember when you try to turn a switch, that's like infinite frequency, going from 0 to something. It blocks all current. So that's why I like to think of this as turning on a switch really fast, inductor dominates. And the other one is in DC. Oops. In DC, the capacitor fills up. So low frequency, capacitor charges up, high frequency, the other thing must be true.
Get out of here. That was good.
We'll do a couple more work problems next time. If you think you know what you're doing, try 31.4. All right. Sometime. Yeah.
Get your phone on acceleration.
Sure.
It's not doing what I want it to. Well,
Okay.
it's the same thing issue I've been having.
Okay.
So I switched this,
Yeah, let me see here.
and then I drag it down.
You got to just drag down this one. You drag down the pair.
Oh, so I don't need to drag down to 0.
So what happens is when you drag down the two cells like that and the two cells aren't the same, it'll keep the alternating pattern dragged down. Got
Okay, that makes more sense.
Yeah.
I was wondering why my graph is all weird. Okay, that's what makes more sense.
Okay. You guys feel like you understand that plot now?
Yeah.
That the weird one with all the crazy symbols and stuff?
Yeah.
Isn't that insane that you can understand all that in 1 2-hour lecture? Jules, you're doing all right? You good? All right.
I'll just.
So Jorstad,
Yep.
I was watching the SBCC lecture.
Yeah, that's a really good
And-
lecture if you haven't seen it, everybody. Okay.
Yeah, it's pretty good. And so he called the RLC or LRC, whatever. He called it a frequency selector, right?
You agree that's exactly what we're seeing?
Yeah.
At certain.
Yeah, exactly.
Yes.
And basically, and then he like used an analogy as a radio, right?
Yes.
So you're setting the tuner, and
Yes.
so what is the tuner changing? Is that changing?
Remember last time when I brought that variable capacitor and the variable inductor,
Yeah.
right? So,
Oh,
right? You could
okay.
literally change where you connect to a coil of wire and change the number of turns you use, sort of like a potentiometer, right?
All right. Yeah.
Remember that? Yeah. And so you could change the inductance and that will change the frequency, or you can
Right.
change the capacitance, either one.
Okay, so
But if
you're
you
so you're
change
literally
LCR,
changing.
Yeah, you literally change the amount of plate overlap or the number of coils used.
Okay, that's kind of cool. And then you change the resonance frequency and basically it lines up with the radio waves getting broadcast, right? And that's going to
Like,
change.
imagine you had a solenoid that looks like this. Can you see what I'm drawing?
Yeah.
Is this kind of, can you visualize this? Like the
Yeah.
front side and the back?
Uh-huh.
The idea is you could connect one terminal right here, and the other one, you could have a drag a sliding contact and connect to any one of these coils.
Okay.
So the idea is if you connect right here, you'd have half the inductance as if you connected right up there, because you have half the coils.
Right. Okay.
And so in this case, you could change the value of L. Or these other ones, what will happen is you'll have a plate here, and we're gonna do this the last week of class, the variable capacitor lab. You could have two different plates. And the idea is you could turn one of the plates and increase or decrease the amount of plate overlap area. And because the
That's crazy.
capacitance is epsilon naught area over D, if you change the area that they overlap, you change the capacitance. Got it?
Yeah, that's cool. All right. Thanks.
And we'll do that the last week in lab when we do the variable capacitors. For the
Okay.
makeup
Yeah.
part.
All right, cool. Thanks.
Is that good?
Yep.
Here, Jess?
Yeah, but I
All right.
see you next week.
Yep.
Enjoy your weekend.
All right, you too, man.